Hello students, and welcome back to another lovely day of chemistry. In today's lesson, we're actually going to start learning about gas laws, and we'll of course learn a little bit about the scientists who discovered those, because that's who the laws are named after. So we have Boyle's law, Charles' law, Gay-Lussac's law, and then actually we'll just combine all of them into one simple law. So Boyle's law is the first one we're going to talk about, and what Boyle's law does is it actually relates pressure and volume. And so with that, he actually first started talking about this like back in the 1600s, just noticing how if you make the volume of a container smaller, such as what you can see over here, what's going to happen is the particles that are moving around are actually going to cause more collisions with the wall. So as the volume of a container gets smaller, particles are being pushed together. And as particles are pushed together, there's more collisions, which means more pressure. Because if you remember, pressure is caused by particles running into the walls of a container. So if you picture something like a balloon, what's going to happen in there is you have all these particles pushing outwards. You have some that aren't always hitting the wall, pushing outwards on the wall of the container. But picture if you were to take that balloon and try and squeeze it down, what's going to happen is those particles are still moving at the same speed. You're not changing their temperature, and so they're actually going to be hitting the walls of the container far more often because they have less distance to cover. So therefore, as you decrease the volume, you're going to be increasing the pressure. And so Boyle's law, we can come up with this equation that P1V1 is equal to P2V2. So I almost just look at this as pressure times volume before is equal to pressure times volume after. So what kind of relationship is this? Well, if we look at the graph, you can see that this is as your pressure decreases, your volume increases. So this is what we would call an inverse relationship. For those of you not comfortable with the word inverse, inverse almost just means like opposite. Essentially, as one goes down, the other goes up. If we can think of, again, kind of like that balloon, think of a real world example. So if we have a balloon that starts off this size, and you can picture if you've ever done this with a balloon or a volleyball or basketball or really just anything that you can squish down, if you take this object, which currently has a pressure and a volume, and that's why I call it before, and now we squeeze that balloon down to a smaller size, that is, as we decrease the volume, you can probably feel that the balloon is pushing back a lot more, which means you increased the pressure. And so that's the inverse relationship. As one thing went down, the other one went up. Alright, and here's a good practice problem for us. So gas tank in a chem laboratory, and we actually have stuff like this. So picture, if you go to fill up your car tires or anything, they'll basically store everything in like a giant canister. And what that is that's stored under a ton of pressure. So that way you can keep it in a smaller, manageable volume, but you store this gas at a really, really high pressure. And in this case, our pressure 1 is going to be 45 ATMs. And the volume that we're storing that in is our 2.5 liters. And so again, it doesn't matter what you label as 1 or 2. Again, I just typically think of it as before and after. So now what it says is we go on, what volume would the gas from the tank occupy at a classroom's pressure of 1 ATM? So basically, what if we were to just take this, open the container, and just let all the gas pour out? What volume would that be able to contain? Or would that occupy? So now we know the pressure 2, and so we could say that P2 is equal to the 1 ATM, and we're going to solve volume 2. So if I were to plug those numbers in, we're going to have 45 ATM times our volume of 2.5 liters is equal to our second pressure at 1.00 ATM. I'll carry that just for the sake of sig figs. Times our volume 2. Divide both sides by our 1 ATM. And we would find that our volume 2 is equal to 112.5 liters. And with sig figs, that would come to, we need 2 sig figs because of our 2.5 liters, so 110 liters. And I should have had you think through this answer first. It makes sense that if you're starting with a really, really, really high pressure, this 45 ATM, so you're going from a high pressure to a low pressure, so that is, as you decrease pressure, what should happen to volume? Well, it should increase. And so our answer makes sense. Alright, so in the previous slides we learned about Boyle's law, which relates pressure and volume. Now we're going to talk about Charles' law, where he's actually going to relate temperature and volume. So remember that really what temperature is it's a measure of the kinetic energy of particles. So it's pretty much just a measurement of how particles are moving or if they're moving quicker. So what Charles determined is that for pressure to remain constant, the volume would need to increase in a sealed container to accommodate the increased movement so there are less collisions. Essentially what he talked about is that if you wanted to heat something up, as you can see here, if you increase the temperature, in order to keep pressure, that is collisions with the container, the same, you would actually have to increase the volume. And so we can see that relationship in the equation here. Volume 1 divided by temperature 1 is equal to volume 2 over temperature 2. Again, just thinking of 1 as being before and 2 as being after. So you can relate the volume and temperature of two different systems if pressure and moles are held constant. So again, what Charles is really doing is assuming that you are keeping the pressure the same and that you are keeping the amount of air, that is the moles, in the container the same. So what is the relationship in this case? Well, if you look at your graph, you can pretty much see that as temperature increases, volume increases. So therefore, this is what we would call a directly proportional, or you could even just say direct relationship, but this is a directly proportional relationship. The simplest real-life example for Charles' law is probably going back to the car tire, right? As temperature increases, you're also going to typically see your volume of the tire increase as well. So again, if you picture your car tire during the winter, you might notice that's a little bit flatter on the bottom. And then, come summertime, it's rounder again because same thing. As the temperature starts to increase, molecules start moving faster, and so they're going to try to expand the volume of the container. Then we start talking about absolute temperature. So temperature in an ideal gas is going to be measured in a unit that we actually call Kelvin. So you'll actually, and maybe you've never heard this before, but you typically hear temperature measuring like degrees Celsius or degrees Fahrenheit. However, when we are talking about gases, we really can't use those because they have negative numbers, because otherwise you would start getting like negative volumes or negative pressures, and those just really don't exist. So we actually have to use this unit called Kelvin, and really all Kelvin is, it's actually a good way to just kind of start at absolute zero. Which, by the way, for those of you that don't know, absolute zero is this theoretical place where molecules have no energy, no kinetic energy, no movement, anything. And so it's really more of in like a perfect situation type of thing. It's more theoretical. However, scientists have managed to get within like a millionth of a degree of absolute zero. Contrary to that, there's actually no absolute hot because, again, temperature just being a measure of the energy of particles, we don't know of a limit for the amount of energy that particles can take, but we do know absolute zero being they have no energy left. So anyway, in order to convert from degrees Celsius to Kelvin, all you have to do is add 273.15. Because really what 0 Kelvin is, it's the same thing as negative 273.15 degrees Celsius. So if you ever are given Celsius in prom, you need to go to Kelvin, just add 273. And here's an example of a Charles law problem. So if a sample of gas has a volume of 1,000 milliliters, when the temperature is 72 degrees, what is the volume when the temperature is increased to 90? So again, 1 is just like your before, 2 is like your after. So we can define our variables. We have 1,000 milliliters is going to be our volume 1. And since that volume applies to this temperature, this is our temperature 1. And then over here we have 90 degrees is going to be our temperature 2. And we're solving for volume 2. What we need to do first, though, is we do actually need to convert this into Kelvin. So I'm going to take my 72 degrees Celsius, add 273, and that's going to give me my Kelvin, which is equal to 345 Kelvin. Then we have to do the same thing with our 90 degrees Celsius, add 273. A lot of times we just simplify and get rid of the 0.15. It's not a big deal. And that'll give us an answer of 363 Kelvin. And then we can plug it in. So our V1 we said is 1,000 milliliters. Over our V1 of 345 Kelvin is equal to X amount of liters, or I should say X amount of milliliters, divided by our temperature of 363 Kelvin. Multiply both sides by 363 Kelvin. Kelvin cancels out, and you end up with an answer of 1,000, and we need to follow our 2 sig figs, so 1,052 milliliters. Rounding to 2 sig figs, we will actually record this as 1,100. I don't know, I guess 90 degrees Celsius is 1 sig fig, so you could record it as 1,000. And that is milliliters. Again, we should always think, does that answer make sense? Well, since we saw an increase in temperature, we went from 72 to 90, then it makes sense that we would go from 1,000 milliliters to, well, I guess 1,050. And then the last of the 3 laws, I know we'll talk combined law next, is just Gay-Lussac's law, where basically as temperature increases, we're going to talk about how pressure increases as well, if volume remains constant. Again, that's important to keep in mind because if volume changes, again, this even goes back to the car tire a little bit, as temperature increases, you notice a change in both volume and pressure because they're going to try and balance each other out. So this kind of assumes a rigid or non-changing container. And so again, Gay-Lussac's law is now going to relate pressure and temperature. So as volume and moles stay constant, so basically as the size and the amount of air remain constant, we can relate the pressure and temperature in 2 different systems. So what is the relationship? In this case, this is going to be, again, directly proportional because as one increases, the other is going to increase. And you can see that looking at the graph. As you go through and increase your temperature, your pressure is going to increase as well. One of my favorite real life examples that most of us have experienced, and it even helps hold true this idea of volume and moles staying constant, is to actually picture your can of pop. We've all probably done this at some point where you go through, you take your can of pop, and you leave it in, I don't know, car on a hot day. What happens? Well, as your temperature inside that can starts to increase, those particles are going to start moving quicker and quicker and quicker and having more and more collisions within that container, therefore causing your pressure to increase as well. And eventually that pressure gets so big that your can now explodes everywhere because it couldn't change. It wasn't able to change the volume to help make up for that pressure, so eventually the can ruptures. Alright, so the gas and aerosol can is stored at a pressure of 3 atm and 25 degrees Celsius. So I have my pressure 1, my temperature 1. But I know you're sitting there saying, oh, Ferris, you gotta convert your degrees Celsius into Kelvin. Alright, so I'll take my 25 degrees Celsius, add 273, and find that is 298 Kelvin. Then where you read on, it says, do not store the can anything exceeding 52 degrees Celsius. So we're going to take our 52 degrees Celsius, add 273, and we find that is 325 Kelvin. And it says, what would the gas pressure be at 52 that causes it to explode? Well, again, that can has a locked amount of moles. You know, it's not going to leak any air. It has a fixed volume. That metal isn't going to expand like, say, a balloon would. And so we have to figure out, well, what pressure is that going to cause it to explode? So we take our pressure 1, which is 3 atm. We divide that by our 298 Kelvin. We set that as equal to X amount of atms, that is our unit of pressure, divided by our temperature 2, which we found to be 325 Kelvin. Multiply both sides by 325, multiply by 325, and we find that this gives us a pressure of 3.3 atms. And again, that one would make sense because our temperature increased, so it makes sense that our pressure increased as well. Alright, and the last thing is our combined gas law, where really we just take all three laws and show how they relate to one another. And it's actually nice. This is really about the only formula you need because you can cross off the other ones if they don't matter. So the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. And realistically, this is the only one that you need to know because if, for example, you are solving a question and it doesn't give you temperature, you just assume temperature is the same, congratulations. You just cross off your temperatures and you're left with Boyle's law, P1 V1 equals P2 T2. Or similarly, if you were doing a question and it didn't give you pressure, right? Pressure just doesn't even factor in, so you're left with Charles' law, V1 over T1 equals V2 over T2. So you pretty much just cross them off if you don't use them. So in this example problem down below, if a balloon with a volume of 1.45 liters at 25 degrees Celsius at 1 atm of pressure, I know it's a lot of things, but we follow our units, and we have a volume, we have a temperature, and we have a pressure, was placed in a room with we have another temperature, and we have another pressure, what would be its new volume? So we start plugging it all in. Same thing, let's convert our Celsius into Kelvin. And so our first one is 298 Kelvin. And then we need to take our 30 degrees Celsius, add 273, and we find that this is 303 Kelvin. So then what we can do is start plugging all of this into an equation. So we have our P1 of 1.0 atm, multiply that by our volume 1, which we defined as 1.45 liters, divided by our first temperature of 298 Kelvin. And we're going to set all of that equal to our pressure 2, which we define as 1.50 ATM, times our volume 2, which is what we want to solve for. And all of that's going to be divided by that second temperature of 303 Kelvin. So now what we're going to do, multiply this side by 303. That way those can cancel out. Multiply this side by 303 Kelvin. Now what we can almost do in like the same step, I guess, is we need to get rid of this 1.50 ATM. So to get rid of something on top, we just divide by it. So divide by 1.50 ATM. Divide this side by the same. And then you can actually watch as your units all cancel out. So ATMs cancel out, Kelvin cancel out, which is good because we're solving for volume and we're left with units of liters. So now when you plug all this into your calculator, you get an answer of 0.98 liters.